is motion all around you, and there are natural laws governing this motion, natural laws that require the brakes to be applied as this train goes around a curve, and natural laws that require this biker to lean into his turn to avoid crashing. There are laws that result in people feeling pulled when going around a corner. There are laws that result in passengers falling forward when a car suddenly stops. And if the car runs out of gas, there are laws that make it hard to get the car moving. All of these examples have to do with the laws of motion, laws that were discovered over 300 years ago by an English scientist and mathematician named Isaac Newton. Newton lived at a time long before cars, planes, and speedy forms of transportation existed, yet he was able to observe the motion of objects around him and develop from those observations the three basic laws of motion. His laws describe how all objects move. Terms such as speed, velocity, acceleration, and deceleration are all associated with a description of motion. The rate at which an object is moving is called its speed. It is measured in units such as kilometers per hour, miles per hour, meters per second, or feet per second. Speed is calculated by dividing the distance traveled by the time it took. So if a car travels 80 kilometers in 2 hours, its speed is 40 kilometers per hour. Velocity is often thought to mean the same thing as speed, but there is a difference. Velocity is not only the speed of an object, but it is also the direction in which the object is traveling. So the proper way to refer to the velocity of an object is to include its direction, such as the car is traveling 40 kilometers per hour south. Velocity changes if the speed or direction of the object changes. Someone racing around a track is concerned with his or her speed. However, an airplane pilot is interested in the velocity of the plane, meaning the speed and direction of flight. Velocity can be changed by changing the speed of an object, by changing the direction of an object, or by changing both the speed and direction at the same time. Acceleration is the rate of change in the velocity of an object. We usually think of acceleration as the speeding up of an object, but there is more to it than that. Acceleration is calculated using the following formula. Acceleration equals the final velocity minus the starting velocity divided by the time taken to change the velocity. Suppose you are in a car traveling at 40 kilometers per hour, and the car accelerates to 45 kilometers per hour over the next second. The acceleration is 5 kilometers per hour per second. Notice that there are two units of time. One is the unit for the velocity of the car, and the second is the time required to accelerate. Acceleration can refer to decreases in velocity as well as increases. If the brakes of a car are applied, the vehicle's velocity decreases, and we say that the car decelerates or experiences negative acceleration. Newton's first law has to do with objects at rest and objects in motion. He noticed that objects at rest stay that way until something comes along to move them. He also noticed that objects that are moving continue to move in a straight path unless a force slows them down and stops them. Newton called this tendency of an object at rest to stay at rest, and the tendency of an object in motion to continue moving, inertia. You must overcome inertia in order to start an object moving. And you must overcome inertia in order to slow down and stop an object that is moving. So Newton's first law of motion states that if no unbalanced force acts on a moving object, the object will continue moving at the same speed and in the same direction. And if the object is not moving and at rest, it will remain at rest until an outside force acts on it. A spacecraft will continue moving through space at a constant speed and in a straight path without the need for engines. Because there is little matter in the vacuum or emptiness of space, there is nothing to slow the vehicle down. Once the craft is away from Earth's atmosphere and its gravitational pull, the engines can be turned off. It will continue at a constant speed and in a straight path. Only if the engine is fired again will the craft be able to change speed and direction. On Earth, objects are affected by outside forces that slow them down and eventually stop them. Even on very slippery surfaces such as ice, objects will eventually slow to a stop. Friction is the force that slows things down. Friction occurs when two objects rub together or try to slide past each other. If you rub your hands together quickly, you will find that within seconds your palms become warm. One of the products of friction is heat. The friction between your palms produces heat. Next time you go for a ride in the car or on your bike, feel the tires after you have stopped. The heat you feel is from friction, produced from the car's brakes rubbing against the tires. Look at the soles of your shoes. You should discover that they're worn down. Where once new, clean treads existed, you probably have worn surfaces. So another effect of friction is to wear things down. The friction between your shoes and the surfaces on which you walk and run has affected your soles. Look at car and bike tires, and you'll also see evidence of wear and tear brought on by friction. So, friction slows down an object until it stops, produces heat, and wears the object down. To avoid the wear and tear of friction on cars, we use lubricants, such as engine oil, to make the engine surfaces slide easily past each other and cut down on heat. If we didn't have friction, things would be very crazy. For instance, the process of walking or running occurs because of friction between our feet and the ground. Without friction, a person at rest or at a standstill could not get moving. And objects that were moving would not be able to stop because they require friction between their surface and the ground to slow down. Here is a computer game for playing billiards. We can turn the friction level to a setting that is very close to zero. Watch what happens when the cue ball is hit into the other balls. All this motion and uncontrolled activity is a result of very little friction. The inertia of the balls keeps them moving in straight paths until they strike other balls or the sides of the pool table. Here is an illustration of inertia. This tablecloth is loaded with inexpensive china and glasses of water. Now watch as we pull quickly on the tablecloth. Inertia is responsible for holding the china and glassware in place. Now, you may not want to try this at home, so here is a version of that same experiment, but only a coin, a piece of cardboard, and a glass are required. Your mother's good china is saved. Here's another demonstration of inertia. A large rock is supported on this person's head. A piece of wood is placed on top, and a friend proceeds to drive a nail into the wood. Why no headache? Inertia. The rock doesn't want to budge. It absorbs the force of the hammer blows, and the person underneath survives unscathed. Now, let's consider the inertia of an object that is moving. When you are riding in a car and the vehicle goes around a corner, you feel like you are sliding off to one side, but actually your body wants to continue going straight as the vehicle turns. We can demonstrate this with this ball and handcart. When the cart turns, the ball rolls off. Now, let's step back and see what is really happening. When the cart turns, the ball continues to travel in a straight path. So when you're in a car and it suddenly turns, your body really wants to continue in a straight line. A spinning gyroscope will resist changing its starting position. It can be balanced on a string or small stand. In the weightless environment of space, the gyroscope works even better. So inertia explains many common everyday situations. Now let's look at Newton's second law of motion. This law describes what happens to a moving object when a force is applied to it. This batter will strike the pitched ball and change the ball's direction. He will try to strike the ball and change its direction. Well, if he does make contact with the ball, the force of his swing and the bat that he is holding will accelerate the ball in a different direction. There, the ball is hit. It travels in the direction in which the force is applied. If the batter hits it straight on, the ball will change direction and travel in the direction of the swing. How much it accelerates depends on the strength of the force and the mass of the ball. Mass is not the same as an object's weight. Weight is a measure of gravitational pull, and it changes as an object gets farther from the earth. Mass doesn't change. It is a measure of an object's inertia. The greater the mass, the harder it is to get the object to start or stop moving. As we add more mass to this cart, the amount of force required to get the cart going increases. Newton found that the higher the mass of an object, the greater the force must be to change the object's motion. That's why we don't play softball with a shot put. There would never be a home run, and bean balls would be lethal. So, the second law of motion says that the change of motion of an object depends on the size of the force and the mass of the object. The greater the force, the greater the resulting acceleration. The greater the mass, the smaller the resulting acceleration. It is harder to stop a train than it is to stop a car, even when the car is moving faster. That's because the train has a greater mass than the car and will require a greater force to slow it down. We say the train has greater momentum. Momentum is the strength of an object's motion. The more mass an object has, the greater its momentum. Momentum is determined by multiplying the mass of a moving object by its speed. The faster an object travels, the greater its momentum. Now we come to Newton's third law of motion. For every action, there is an equal and opposite reaction. A rocket uses that principle to blast off of the ground. As fuel is burned and gases shoot out of the nozzle of the rocket engine, an opposite and equal force moves the rocket upward. Here is a cart containing a heavy metal weight and a strong rubber band stretched tight and ready for release. What do you think will happen when the string that holds the rubber band is burned through? As you may have guessed, when the string breaks, the rubber band causes the weight to fly off in one direction, and the cart goes zooming in the opposite direction. These rocket cars are powered by CO2 cartridges. When the nail punctures the end of the CO2 capsule, CO2 gas escapes out the back. The cars go zooming forward. The cars move in an opposite direction than the escaping gas. Roller coasters and other amusement park rides are based on the laws of motion. The wild turns are designed to take advantage of inertia and another force called centripetal force. We will show an example of centripetal force using this flat piece of wood and this glass. The glass will stay on the piece of wood while spinning around and around. Even when held overhead, the glass stays in place on the board platform. How would you explain why the glass remains on the board? Newton's second law of motion explains that the glass and board want to travel out away from the person. They want to travel in a straight line, and if we let go of the rope, that's what will happen. The board and glass fly off in a straight path. So the rope is holding the board and glass inward and in a circle. The glass, because of inertia, wants to fly away, but the bottom of the board is sturdy and holds the glass in place. The force required by the person to hold the rope inward and to resist the outward straight-ahead motion of the board and glass is called centripetal force. If you don't want to risk breaking a drinking glass, try this. Bend a coat hanger as shown, and then hold it with one finger as demonstrated. Carefully place a coin on the tip of the hanger hook and begin to spin it. It may take a few tries, but it is possible to spin that coin with grace and ease. You have experienced centripetal force and inertia if you have ever been on amusement park rides like these. A roller coaster ride can carry you upside down or through a series of loops without ejecting you because of inertia and centripetal force. Today we have looked at the 3 laws of motion described by Isaac Newton back in the 1600s. Newton's first law of motion states that an object at rest will stay at rest, and a moving object will keep moving at the same speed and in the same direction, unless an outside force acts upon it. His second law of motion states that an object accelerates when a force is acted upon it. The stronger the force, the greater the acceleration. The greater the mass of the object, the larger the force must be to accelerate the object. And Newton's third law says that for every action, there is an equal and opposite reaction. While talking about the laws of motion, we have also discussed friction, which has a dramatic effect on moving objects. Friction occurs when 2 objects rub together. It slows down the objects and produces heat and wear. We also talked about centripetal force, which is the force experienced when holding an object in orbit. Now it is time for the program quiz. Question number 1. Newton's first law of motion is also referred to as inertia. What is inertia? Question number 2. Newton's second law of motion talks about changing the acceleration of an object by adding or applying a force. The greater the blank, the greater the acceleration. The larger the blank of the object, the greater the force required to accelerate or slow down the object. Question number 3. What is Newton's third law of motion? Question number 4. What force makes us move forward when a car stops suddenly? Question 5. Name some ways that friction can be helpful and some ways it is harmful. Question number 6. What force holds an object in a circular orbit? Question number 7. Why is it harder to stop a train than a car, even when the car is moving faster? Question number 8. Describe how mass and weight are different. Question number 9. A spacecraft traveling in space can travel at a constant speed and in a straight path without using engines. Why? Question number 10. How is momentum calculated?